We've singled out first order reactions because in fact those are the ones that we see most commonly, and it's also something that shows up in other kinds of rate processes like radioactive decay. I want to repeat a central feature of that, and that was that the half-life of a first order reaction related directly the rate constant K and the half-life T. So in fact they give us the same information. And a question that we might ask is this generically true? Is this true of other orders? So in order to answer that, we need to look at some different orders of reaction. So in this video we'll talk about first zeroth and second order reactions. So a zeroth order reaction is one which would have a rate law that looks something like this. The rate is going to be minus the change in the concentration of our reactant A, which is going to equal to K raised with A raised to the 0 power. That's where the zeroth order rate constant comes in. But anything raised to the 0 power is just 1, so it's just going to equal K. So what this is telling us is that this reaction is one that has the same rate no matter what the concentration is. You might say, well, how can that ever be? What sort of reaction would that be like? It turns out that certain enzyme catalyzed reactions follow this sort of rate law, so it's not unheard of and can occur. Now, it's also a particularly easy equation to integrate. So in fact, if I do the same substitution and say that x is the same as a at some time t, then I could write this as dx is equal to minus k dt, and if I integrate this both sides from sometime 0 to sometime t, and I'll let x go from my initial value to my final value, well, the integral of dx is pretty easy, and so is the integral of dt. So this is perhaps the simplest equation to integrate. We'll have that the difference between the time t value and the 0 value is just equal to minus k times the time. All right, so when we want to write down the integrated rate law for this, it comes very simply that a at time t is just its initial value minus kt. And so that is our integrated rate law. Now, if we were to graph this, that's also a very simple graph. And I won't spend a lot of space doing this, but time and concentration is just going to be a straight line down from the initial value up here down here. And obviously something has got to change when it hits the bottom here and we run out of reactant. That's basically where the reaction is going to end. All right, how would we describe the half-life in this case? Since we found this relationship for half-life of first order reactions, what will be true for zeroth order reactions? Well, again, it's where this value is equal to 1/2 of this value. So if I were to simply subtract those two, I would find that minus 1/2 of the initial value, if this is 1/2 A0, minus 1 A0 is minus KT 1/2. So I can simply relate that T 1/2 is equal to 1 over 2 times the rate constant times the initial concentration. All right, now you'll notice that one thing that is different about this one is that it depends upon the concentration initially. So in other words, this half-life is going to depend on what's there initially. So if I go down one half-life to here, I'll have a certain time. Now if I go down another half-life to here, you'll notice that the gap between these two is much shorter than the gap that it was for the first one. So in other words, the second half-life, and I'll write that with a superscript 2, is less than the first half-life. And in fact, what generally happens is that successive half-lives, in the case of a zeroth order reaction, are shorter. All right, that's really all I want to say about zeroth order reactions, because I think it'll be more interesting to look then at second order reactions and how they might differ. So for a second order reaction, how will we write down the rate law? All right, in this case we'll have rate, and again we'll just have equal minus the reactant change in the reactant, is equal to K times the concentration of the reactant squared. So it's the power of 2 that makes this a second order reaction. So again, if we're going to use X as our stand-in for A, what we'll have is minus dx dt is equal to kx squared. So now rearranging this, what I'll have is minus dx over x squared is going to be equal to k times dt. And now if I want to integrate this to get the integrated rate law, I'm going to go from my initial value of the concentration to my value at time t. So I'm going to be integrating time from 0 to t. So now when I figure all this out, the integral of 1 over x squared is minus 1 over x. So that will cancel the minus sign out front here, and I'll have that this is simply 1 over x evaluated between these limits. So it'll be 1 over a at time t minus 1 over the concentration of a at time 0. And the integral of this is the same as it's been in all the others. It'll just be kt. So this is now our integrated rate law for a second order reaction. All right, so how does this vary? Well, first of all, one of the things that we want to look at here is that as time gets longer, that means that this side of the equation must get bigger. But it can only get bigger if this value, this concentration of A at time t, is smaller. In other words, as this decreases, that will increase time. So if we were to graph this out, and I'm going to try to draw this carefully, but I may not. So this is time, and this is again our concentration of A. It'll start off at some initial value, and it will come down, and it decays to 0, but it doesn't decay as strongly as it does in a first order case. All right, so we'll see a gentler slope, but it's still ultimately decaying to 0. Now, what does this do in terms of half-lives? If I am interested in the half-life, then I want to take 1 over 1/2 A0 minus 1 over A0 is equal to k times t sub 1/2. Okay, but this is just going to be 2 over A0 minus 1 over A0, so I'll have that this is equal to 1 over A0, or my half-life is going to be equal to 1 over k times the initial concentration. So once again, as we found in the 0th order case, our half-life is going to depend upon the initial concentration of A. But now, as that initial concentration of A gets smaller, t sub 1/2 is going to get longer. So in other words, the second half-life will be longer than the first half-life. And indeed, when we go to the graph here, if this is the first half-life, so this is 1/2, and now I go down to the next one, 1/4, this gap here is going to be greater than this gap. It's actually going to be twice as great as that gap, as one can prove mathematically using this expression for the half-life, this expression here for the half-life. All right, so we see that as we go from first to second to 0th order reaction, we have a definite trend in the behavior of successive half-lives. And in fact, what we find is that for a 0th order equation, for 0th order, the second half-life is always less than the first half-life. For a second order equation, the second half-life is always greater than the first half-life. And in the case of a first order equation, they're equal. So you can think of this as being like a trend between the successive half-lives. And this also is a way of recognizing different kinds of processes. If you have enough data that you can identify the half-life of a process, a reaction, or some other process, then you can sometimes, just by inspecting the length of the successive half-lives, you can determine what the order of those processes are.